All right. Well, if unless there are no oppositions, I think we can just get started. So it's my great pleasure to introduce Pengzi Miao from the University of Miami, who from whose papers I always learn a lot. Today, we're very lucky to have him talk about some remarks on mass and quasi-local mass. Please.
Thank you, Martin. Thank you for your introduction. And also, I would like to thank all the organizers for organizing this excellent event. And in this talk, let me start by giving you the plan of this talk. So in the first part of the talk, I will be talking about some work on detecting mass via polyhedral on both asymptotically flat and asymptotically hyperbolic manifold. And this part of the work of the talk is mainly based on two separate works. One is with Anakera Piubello, and the other one is with Dr. Hengcheng Jang. And the second part of my talk, I will talk about some recent estimate on Bartnik's quasi-local mass. And that part is based on joint work with Anakera Piubello. All right, let's start by recalling the definition of asymptotically flat manifold and its mass. So Riemannian 3 manifold is called asymptotically flat if there exists a chart outside a compact set in which the metric satisfies suitable decay. And moreover, if the scalar curvature is integrable. On such a asymptotically flat manifold, the ADN mass put forward by Arnold, Desire, Misner in 61 takes this formula. And it's a result by Bartnik and also independently by Crucial in 86 that this quantity, the ADN mass, is actually a geometric invariant independent on the choice of coordinates. Now, I do want to say this expression from a physical point of view is very natural because it arises from the Hamiltonian formulation of general relativity. On the other hand, for a geometer, maybe it's not that obvious on the first look to get its geometric insight. I remember I struggled with understanding this formula when I was a student. So here is an observation I made about 2 years ago by now. So if one is given an asymptotically flat 3 manifold, the previously defined ADN mass given by this formula 1 can be read from certain geometric data. When I say geometric data, I probably was cheating a little bit because I do make use of reference to coordinate chart. Now let me explain this formula 2. So on a asymptotically flat manifold, one can look at one can take a large coordinate cube near infinity. And this cube has its faces and has its edges. And on its face, one can compute its mean curvature with respect to the metric G. And along the edge, one can measure the angle between, say, the two normal vectors on the adjacent faces. And the observation here is if one compute the mean curvature and if one compare the difference of the angle with its background value, which is 90 degrees, and the sum of these two integrals recovers the mass as this cube becomes larger and larger. This statement, this formula 2, as you can see, itself does not involve harmonic functions. However, I do want to emphasize that the discovery of this relation 2 actually was motivated by Daniel Stern's work in 2019, where he made intriguing discovery between scalar curvature and the level set of harmonic functions. Now, once one has this relation 2, it's natural to ask what can be said on other polyhedral. Before we come to that question, I want to give you some example. And the example here, the purpose of this example is mainly to illustrate the role played by the angle along the edges. For example, we can look at the usual Schwarzschild metric in conformally flat coordinates. Now, in these coordinates, the metric is conformal to the Euclidean metric. Therefore, the angle is identical to the Euclidean background cube. So if you take a coordinate cube in this conformally flat coordinate, the angle along the edge does not make any contribution. In the meantime, for the same Schwarzschild metric, one can write it in the so-called rotationally symmetric coordinates. In this coordinate, if you take the standard coordinate cube in this coordinate in which the metric is rotationally symmetric, you can indeed check the angle does make a contribution. So the point here is to show in this asymptotically flat case, these two integral themselves are not geometric quantities. The sum passing to the limit is, but the limit of each individual part is not. The reason I want to make this remark is because very soon, later in the talk, we will see that the story is rather different in the asymptotically hyperbolic setting. So that's mainly the purpose of these two examples. Okay, having said that, we can move to the more natural question. What about you replace the cube by a more general polyhedral? And this is the work done together with Anna Chiara Piubello, who is my current PhD student. And we consider asymptotically flat manifolds in. Yes, please.
Excuse me. There is a hand raised by Christina.
Oh, yes. Let me.
I have a question for your example.
Yes, Christina. Yes, let me go back.
Yeah. The mean curvature in those examples.
Right.
Can you tell us a little bit about that?
Well, okay, you know, because we are looking at the cube, right? So if you take a cube, oops, yeah, I'm trying to draw things, so I need to switch mode. Now the face of a cube in particular lies on a coordinate plane. So,
right.
So from Shen Yao's proof of the positive mass theorem, we would know that, say, if the mass is positive, then the mean curvature, let me use mean curvature vector. So the mean curvature vector got to point towards infinity. Right? Assuming the mass is positive, then the mean curvature vector.
Okay, so the mean curvature is pointing outward in these examples, because these are very similar to Gromov's cube inequality approach to scalar curvature.
Yes, in a way.
So it's I would consider these to be geometric. It's just that the cube is changing its shape on the two pictures, right?
Right. Yes. Yes.
Yeah.
And also the angle changes in these two pictures.
Right. Right. But the particular cube being considered is different because.
That's right.
Yeah.
The cube do changes. Yes.
Yeah. But I mean, it's diffeomorphic to the other cube. But okay. Yeah. Okay. Great. Thank you so much.
All right. Thanks. All right, so in the result with Anna Chiara, we consider an n-dimensional asymptotically flat manifold, and we look at a sequence of Euclidean polyhedral. Now, what do we mean by Euclidean polyhedral? It's really a polyhedral in the background, Euclidean space, in the Euclidean coordinate chart. And there will be some conditions to impose on such a sequence, which we will mention it in the next slide. So here basically is if you take such a sequence of polyhedral expanding to infinity, then you have this expected relation telling what the mass is by looking at the total mean curvature on the face of each polyhedral and the integral of the difference between two angles. And you may notice that here I changed notation. Previously, I used the angle given by two normal vector to the face. Here, for convenience, I use alpha to denote the so-called dihedral angle formed by two adjacent faces. So picture-wise, if that's your polyhedral, then this is the angle. All right, now let me explain the conditions needed here. And by the way, as you can see from this illustration, in this statement, there is no assumption on the polyhedral type. We can so this sequence can be a mixture of cubes, tetrahedron, or octahedron, etc., provided they satisfy suitable conditions. And condition 1 here says basically the sequence form an exhaustion sequence of the manifold. So here the unit R sub pk denote so we assume everything includes the coordinate origin. Therefore, we use this minimum coordinate length as a criteria, as a comparison unit. And then we assume that the area of each face of the sum of all the face grows like the quantity we expect. So it's a big O times R pk to the power n minus 1. Big O here means the constant C involved is independent on K. And similarly, one expects that the total volume, the total n minus 2 volume of the length adding up is a big O of R pk to the power n minus 2. And there is a technical assumption which I think it's possible may not be needed. Here we impose it for the proof and for the purpose of our proof. Here alpha bar is a Euclidean dihedral angle. So it's such an angle. You take a polyhedral and you look at its dihedral angle between two adjacent faces in the background Euclidean coordinate chart. The thing we want to rule out is we do not want such an angle to become thinner and thinner. Our result does allow the polyhedral to be non-convex. So if you look at such a non-convex configuration, this is the picture we want to rule out. So either it cannot be like a sharp edge, or it cannot like go all around. Again, I believe this D. Yeah, I do not know if this condition D can be improved. Now, as an application of this result, in particular, one can start from a fixed, say, octahedral in a coordinate. Well, I have trouble identifying which polyhedral corresponds to which name, octagon, etc. So let me just use tetrahedron. So if you start with a fixed tetrahedron and then you scale it in Euclidean background, then as the scaling factor become large, you can detect the mass along such a sequence formed by the scaling of a fixed tetrahedron, because all the conditions we imposed are satisfied. Okay, let me say a little bit about the proof of this relation. The basic tool we use is a formula measuring the difference of two mean curvatures for two metrics which are close. So here, sigma is say a hypersurface in a fixed open set U. and one consider two Riemannian metric. The metric G bar will denote a background metric, and the physical metric G will be assumed to be a perturbation of the background metric, and we assume the perturbation is small, measured by a constant depending on the dimension. Assuming this H is the perturbation is small, a direct calculation gives this relation. So the mean curvature of the physical metric subtract the mean curvature of the background metric of this hypersurface sigma with respect to the same size is given by the following expression. Now, if one is familiar with the mass, the integrand in ADN mass definition, one immediately see the first part corresponds to the integrand of the ADN mass integral. And then you have a divergence term. The divergence happens on the surface sigma. So here, divergence gamma bar means the divergence on the hypersurface with respect to the induced metric from the background metric. And then you see the second fundamental form part. The second fundamental form of this hypersurface in the background metric matched or compared or a product with the deformation on this hypersurface. And then one has some error term. Given this relation, one may expect the first portion will pick up the mass term. Then the second part, upon integration by part, probably will produce quantities that relates to the angle. It's not identically the angle quantity that we see in the previous slide, but it's a term that relates to it. Now, if you look at this, if you continue to examine this quantity, you see the second fundamental form. The second fundamental form of the hypersurface in the background. And it's this second fundamental form that I think that suggests the use of a hyperplane. Because the background is Euclidean space. If you look for the simplest choice of a hypersurface, which would simplify this relation, you take a hyperplane whose second fundamental form is 0. So those term drops, and then you carry out calculation, and then you can prove the formula that we mentioned. Now, it would be curious to ask, what if you do not choose hypersurface, if you do not choose hyperplane? Well, other hypersurfaces with relatively simpler second fundamental form would be round spheres. So for curiosity, one may ask, what happens if you plug in the coordinate sphere, the usual candidate where you compute the mass integral? Well, if you plug in such a candidate into this relation, you obtain such a expression telling the mass. So here, the first one is the integral of the two mean curvature difference on the coordinate sphere. H bar represents the mean curvature computed with respect to the background metric, in which case we do know the value, n-1/r. And similarly, the second term is the difference in the change in area. Again, the area of this background surface in Euclidean space is known, is the constant omega n-1 times r to the power n-1. So, so this is just a remark on what happens if one wants to go back to use the standard surface, which is coordinate sphere. All right, let me see. Okay, before I continue, before I move to the asymptotically hyperbolic manifold, any questions?
Is there a relationship between this and Chertam?
Between which one? Between
This sort of the spherical.
Yes, between the spherical case, the equation
Yeah.
4. Yes,
Yeah.
yes. You see, one sees this term, right? One sees the first integral, right? Yes, indeed. I thought about this. I think there is a relation. So in Brown-York mass, mass, in 3 dimension is integral of h0 minus h. So the only difference here is this is the mean curvature produced by isometric embedding of the coordinate sphere, and this is just simply the coordinate mean curvature. Now, now not in Shitan's paper, but in another paper, Fan Shitan, right? So Shitan together with Xuqian Fan, they prove that the limit of Brown-York mass goes to ADN mass, and there, I think this formula can simplify one step used in their proof of the Brown-York mass goes to ADN mass.
Thank you.
Yeah. Thanks. Okay, so because our previous 2 talks in this morning are both related to asymptotically hyperbolic space, so let's ask, what about asymptotically hyperbolic manifold? And as I said, this part of the work is based on joint work with Hin-Chun Jang, which I'll write the theorem in a few slides. So first, let's bring some setting. So we use Hn to denote the standard hyperbolic space with this metric written in the spherical symmetric form. And following the work of Crucial and Herzlich, one says a manifold is asymptotically hyperbolic if there exist complex sets in your physical manifold and in your model, so that complement of these 2 complex sets, you have a diffeomorphism. And once you put back the metric, you put the physical metric to your background space, the metric decays according to suitable conditions. And moreover, like the asymptotic flat case, for the mass to be defined, we need the integrable condition on the scalar curvature, which in this case is scalar curvature minus negative n minus 1 times the weight r is finite. Okay, and now let's recall what are the mass function on such asymptotically hyperbolic manifold. As Piotr mentioned in his talk, on asymptotically hyperbolic manifold with the sphere being conformal infinity, the mass is actually a collection of linear functionals, or you can think it's as a linear map from this space, known as the static potentials on the hyperbolic space. The static potential space is spanned by all the coordinate function if one think the hyperbolic space as the paraboloid sitting in the Minkowski space. So the mass functional is given by the following integral. Whenever you plug in a static potential in this space, and then you consider this limit along coordinate sphere given by the length of z equals r. Naturally, having seen the previous relation between the mean curvature of 2 nearby metric, naturally one may wonder how such a relation can help one to understand this integrand. So that's something we will consider next. Okay, so let this notation be given as same as before. And now we have an extra ingredient, so given a function, and one can consider a corresponding one form, which appears in the integrand of the mass functional. And if the perturbation is small, using the relation of these 2 mean curvature formula, one can derive the following relation, which you may view it as a weighted version of relation 3. So the mass one form used in computing the mass integral consists of the weight function v multiplied with the mean curvature difference, then the divergence on the hypersurface sigma of some vector field together with this weight, and then you have the remaining part besides the error term. In particular, one would be interested in, in analyzing this term circled in red. So for convenience, let's give it a name. Let's call it AV sigma, because it involves the hypersurface, the background hypersurface sigma you choose. I mean, when you try to compute this flux, the flux of this one form across a background hypersurface, you need this sigma, and also you want to make a choice of the function. So this quantity depends on v and sigma, given by 6. Now in 6, the metric deformation on the hypersurface is again paired with the second fundamental form of sigma, and then you have the trace of the metric deformation on the hypersurface sigma. In general, it's not clear how to handle these two terms, so one may try to make some simplification. Going back to the asymptotic flat case, the static potential there is chosen to be 1. Therefore, we already see taking sigma to be hyperplanes is a natural candidate. Now, in the asymptotically hyperbolic case, because one want to control or one want to analyze this one form, so we can start by making simplifications. So let's consider those hypersurface in the hyperbolic space, so that they are totally ambiguous. Because otherwise, it may be challenge. It's quite challenging to handle the term A, B, sigma. So let's make this simplification, and then this quantity takes the following expression, assuming the function v is not 0. And therefore, if we want to get rid of it, we would be seeking a pair, a function v and a hypersurface in hyperbolic space, so that we want to see if this condition can be met. Okay, so with this in mind, one notice that some direct choice of such a pair, simplifying the quantity A, can be conveniently described in the half-space model of the hyperbolic space. So let's use y coordinate to denote hyperbolic space in a half-space model. And we know the metric is conformal to the Euclidean metric with a conformal factor 1 over y1 squared. The interesting feature of this model is in this coordinate, 1 over y1 is t minus z1, where t and zi are coordinate we mentioned earlier for hyperbolic space in the as a hyperboloid model. So, and because we know t and z1 are both static potential, therefore 1 over y1 is a static potential. So one may be motivated to plug in this choice of y1 inverse into the mass functional. Another thing one notice here is, if one takes sigma to be the level set of y1, say in this picture, if you take sigma to be the level set of y1, we know it's a so-called chorosphere in hyperbolic space with constant mean curvature n-1. So here, when we say the mean curvature, we mean the mean curvature taken with respect to direction pointing towards infinity. And moreover, one also notice that if you take sigma to be, oops, by the way, this does not extend beyond y1 equals 0, so I stop there. If you take sigma to be a level set of other y coordinate functions, say y alpha is not 1, then such a hypersurface is totally geodesic in Hn. And one can check that in both cases, that quantity A, B, sigma is 0. Well, with this in mind, one may go ahead to apply the previously derived formula regarding this one form UV on hypersurface sigma to the choice of such a y-coordinate prism. And that's the result together with Dr. Hinchun Jang. So we consider MNG be asymptotically hyperbolic, and let P sub L denote such a y-coordinate rectangular prism. And along the y1 direction, the coordinate y1 direction, we consider this range, y1 goes from e to the power negative L to e to the power L. In case you may wonder, why you choose such a range, because in our estimate, we carry out the calculation in the so-called in the model where the hyperbolic metric is written as dx1 squared plus e 2x1 times dx2 squared plus dxn squared. So in that coordinate, in x coordinate, we just take a rectangular prism centered at the origin. Going back to the y coordinate, we see why that's the reason why we have these two. And then why I want to use a parameter?
Excuse me.
Yes.
There seems to be something happening with your sound, or maybe it's on the side. Now
Okay.
it seems to be fine.
Okay. Oh, thanks. I hope it's not my internet. I'm hoping it's not the internet problem. I'm in my office. Usually the internet is fine, but yeah. Well, thanks.
The problem seems to have gone. So
Okay. Well, thank you for letting me know. Yeah. Okay. If something is missed, I'll repeat it. Yeah.
Sure. Thanks.
Thank you. Right. So along the y1 direction, we can choose this EL or e to negative L as a reference. Then we you have this horizontal direction in this coordinate chart. So let's use a quantity sigma L. The sigma L here, sigma L is a function defined for large L that goes to infinity. And so far, that's the only restriction one need to impose on sigma L. And then following the earlier observation that 1 over y1 is a static potential corresponding to t minus v1. So plug this into the mass formula. One conclude that the mass component along the time direction subtract the mass component along the z1 direction in the hyperboloid model is actually given by such integral up once you pass to the limit. Now, this relation may not, let me say this, relation can be better illustrated once we pass to the Poincaré-Bourg model. Because in the Poincaré-Bourg model, you probably see the Z1 equals infinity direction more explicit. In the half-space model, y1 equals infinity. It goes all the way vertically up. So for that reason, we can switch to the Poincaré-Bourg model. And then this is, that's V1 equals positive infinity. And what this relation said, what the polyhedral PL, which looks rectangular in the y coordinate, now looks in the following shape. The more interesting thing here is if you let this parameter length sigma L to grow suitably fast relative to some quantity given by e to the L times n minus 1 Q. In particular, if you look at those space where the decay rate is bigger, it's faster than n minus 1, like the ADS Schwarzschild, then this condition is not needed. And under such assumption, you notice the following. I'll try to draw it on the picture. The angle in this coordinate polyhedral, does not make a contribution. Moreover, the integral on the face of that part, which maybe I should color it in. Let me see, using another color. So the integral, the face integral on this part, on that part, also goes to 0 in the limit. So the only thing that survives is the integral living on the larger Hauss field, on the portion of the larger Hauss field. So that's something one observed by direct calculation. And again, under the assumption that if this coordinate length is relatively large, in particular, that condition is automatically satisfied if you are working with a hyperbolic space where the decay rate, say Q equals N, like ADS ratio. And this is the reason that why I mentioned the two examples back in the asymptotic flat case for the Euclidean, for the asymptotic flat Schwarzschild case, because there we see sometimes if you choose your coordinate chart or coordinate polyhedral or even cube, if you choose it differently, you see the angle contributes sometimes or not contribute sometimes. But in the asymptotic hyperbolic case, you see they do not make a contribution. All right, now this suggests a related formula, again, obtained with Dr. Jang. So this formula says if you can look at the difference between the mass component along the time component and the Z1 component, and this difference can be completely measured or computed via integrals happening on such a Hauss sphere. So here H script HL is the level set of Y1, say Y1 equals constant E negative L, and one perform an integral, a weighted integral with V being this weight T minus Z1, which points to why you have this difference on the left. And the relatively geometric quantity is the mean curvature difference again. Also, if you draw this Hauss sphere in the Polyhedral model, you notice that this Hauss sphere is tangential visually to the infinity at Z1 equals positive infinity. So heuristically, they said if you take this blue, if you look at this blue round coordinate sphere in this Polyhedral model, such that it's tangential to a point near conformal infinity. So here I'm using the word conformal infinity, even though the asymptotics needed here is weaker than conformally compact manifold. If you consider such a figure, then you can detect the energy or the mass component along t direction minus mass minus z1 direction. Now, in case one may wonder, could this allow you to discover every component of the mass functional? The answer would be yes. And for example, if you choose another point, say the opposite point in this Polyhedral model, and then you just repeat this construction for another Hauss sphere, and then you would get mt plus mz1, and then you read every mass component. So far, all these results are based on direct computation. In particular, there is no scalar curvature assumption imposed. Now, if one impose scalar curvature assumption on the asymptotically hyperbolic manifold, then one can invoke the positive mass theorem together with its rigidity. In Crucial's talk, we see a rich development about positive mass theorem on asymptotically hyperbolic manifold. So if one apply the known result there, one may get a corresponding rigidity statement of asymptotically hyperbolic manifold. For example, if the metric is hyperbolic outside such a coordinate Hauss sphere, under the scalar curvature assumption, then you get the rigidity. Now, before I move to the second part, I do want to mention some other research along this direction. In particular, in the asymptotically hyperbolic case, Xiaoxiang Chai, he made further interesting progress. So Chai found that actually the quantity that I mentioned earlier, this A, V sigma is indeed 0 for any y coordinate hyperplane, using the fact that the metric, hyperbolic metric in the y space is conformal to the Euclidean space. And Chai found that this quantity is 0 for any y coordinate hyperplanes. And as a result, he can have analogous formula for general y polyhedral. And in another context, in the asymptotically flat case, if you include the k term, so on a general, possibly non-times metric initial data set, a relation between the energy momentum vector and the polyhedral was obtained by Ken-Yu Cang. So as I said, before I move on to the next part, I do want to mention this nice work. Okay, any question before we proceed? Okay, I don't think I have enough time. So, I don't think I have.
There is a hand.
Okay, but yeah. So let me try to
Pengzi, there is a hand by Xiaoxiang.
Oh, okay. Yes. Let me. Yes. Oh, yes. Please. Do I need to?
No, you're fine. He should be able to start talking. I mean.
Okay. Yes. Yes. Xiaoxiang,
My
please.
question is,
Yes.
You obtain the mass only on Hora spheres. Is there any notion like you perturb the Hora sphere a little bit, you get like almost Hora spherical
Yeah.
mass approximation?
Well, so this relation 8 is one of the consequence of the relation given by this line. So in particular, if we in this space, right? If we in this configuration, in this picture, so to read the math, all one need is the following: is to get information on a family of such horizontal hypersurface which go towards infinity. So in particular, if you make a full use of this quantity sigma L, one could see that you do not need the metric to be, so in other words, you do not need all the information on the coordinate Hora sphere. You only need such a portion, which probably my picture is not that well. So let me enlarge it a bit. So you only need the portion of the metric. You only need the information of the metric on the portion of each Hora sphere illustrated in this picture. So far, I don't know about other more precise region where you can derive such a similar formula, but I would think so. Yeah, I would guess such things exist. I think that's probably more related to what you ask, Xiaoxiang.
Okay, thank you.
You're welcome. All right, so use my hand. Okay, now, all right. So in the remaining part of this talk, I want to briefly talk about some recent estimate on Bartnik mass. So I'm switching the gears here. And part of my motivation here is this part of the talk is based on my joint work with Anna Chiara Piubello. And Piubello is going to participate in the workshop in May. So in a sense that this part may be maybe a prelude to her talk in May. Okay, so let's have some notations. So sigma is a closed, connected orientable surface, and gamma is a Riemannian metric on sigma, and h is a function. And we say such a triple admits a non-negative scalar curvature filling in if, essentially, if the following picture holds. So if you start with this triple, the surface sigma with a pair of metric and mean curvature, if you can find a compact asymptotically compact manifold with non-negative scalar curvature, so that the boundary metric is gamma, the boundary mean curvature is h, then you call this triple admits a non-negative scalar curvature fill-in. Usually, when people talk about Bartnik mass, people want to start with extension. Here, I do prefer to first assume that the so-called Bartnik data admits certain fill-in to start with. And then let's talk about the Bartnik mass in the time symmetric case. In the non-time symmetric case, yesterday you see the elegant presentation by Lan Xuan already. So here we focus on the time symmetric case. The Bartnik mass is defined to be the Simon of the ADN mass of an extension mg. Here mg is legitimate if it has non-negative scalar curvature. The boundary is isometric to the given surface, and under the isometry, the mean curvature is h. So this is like a due to the description of fill-in. So now you consider all the extension satisfies the boundary condition. Moreover, often one assumes some non-degeneracy condition, say no horizon in the extension, to preclude the case that the mass can be made arbitrarily and positively small. One reason that I like the filling in condition is if you assume that this triple admits a non-negative scalar curvature filling in, then by the positive mass theorem of Shen-Yao and Witten, the Bartnik mass got to be non-negative. Okay. Okay. Here is a brief collection of the known result concerning an upper estimate of the Bartnik mass. We use a notation K to denote the Gauss curvature of gamma. Assuming the Gauss curvature is positive and the mean curvature is positive, as a corollary of their beautiful work on the positivity of Brown-York mass, Chitan's method actually gives an upper bound of the Bartnik mass under this assumption, and it's bounded by the so-called Brown-York mass. Here, H0 is the mean curvature of the surface isometrically sitting in R3. I'm going to talk about this estimate in a little bit more in the next slide. But first, let me mention that in a very important case where the mean curvature is 0, so here the Bartnik mass is a functional of a pair, gamma and h. Now, assuming this function is 0, Mantolides Shen proved that if the metric satisfies this geometric condition, lambda 1 of this operator negative Laplacian plus Gauss curvature is positive, then the Bartnik mass is bounded from above by 1/2 of the area radius. Recently, Chow and Martens showed that this estimate remains true in the borderline case. If lambda 1 equals 0, Chow and Martens prove that this estimate still holds. And one may say, if combining this with the Penrose inequality by Bray and Huskin in Manon, then this case, h equals 0, one knows precisely what the Bartnik mass is. In other cases, if h is taken to be a constant, we have a series of work along this direction. We have the result by Lin and Somani, we also have some other related work by Cabra, Pacheco, Siddebang, McCormick, and myself, and Wang Xie mean, and also Charles-Martins. I think the most recent estimate on the CMC case is given by Charles-Martins. All right. The motivation for the remaining discussion is motivated by the following case. So if, right, so we know that the Bartnik mass concerns this pair. Mantelitius-Shen's case considers H equals 0. You may ask what happens if you make the other variable special. Yes, one can consider that. So if you take the metric to be the extreme case, say the round sphere, and then you allow the mean curvature to vary. Now, of course, this case would be much simpler because you do not like you take the metric to be the simplest one, and here all the flexibility is a function. So this would be much easier comparing to the other case. Okay, an observation in this special case I had back to 2007 is, in this case, the Bartnik mass is bounded from above by this quantity. Now this quantity may look like the Hawking mass, but it's not exactly, because you see this is the integral, this is the square of the L1 norm of the mean curvature. So the claim, well, I tend to think that in this very special case, this estimate 10 is optimal in the following sense. First, this estimate is achieved if your mean curvature is also constant, right? So you take the rotationally symmetric data, the metric is round, the mean curvature is constant, say the sphere, the rotationally symmetric sphere in Schwarzschild, then you know the Bartnik mass is given by its Hawking mass, which agrees with this right-hand side. So the inequality is obtained in these cases. And moreover, one can compare this term with the term obtained by using isometric embedding in the work of Shitan. And one can check that in this extreme case where the metric is round, this bound is strictly less than the Brown-York mass bound, unless the so-called mean curvature radius is the area radius. In this case, if you assume the data bounds a non-negative scalar curvature fitting in, though you know the relation 11 is always holds unless your data arises from a round ball in R3. Now, having noticed that, we want to make some generalization of this estimate 10. So 10 is an upper estimate of Bartnik mass. In the special case, the metric is round. And we would like to say if there can be some generalization to include more metrics. So here is the result obtained with Anakera. So let gamma be a metric with non-negative Gauss curvature, and H be a positive function, and R sub gamma be the area radius of the metric. And then the Bartnik mass satisfies the following bound. So in this bound, the first factor is 1/2 area radius. Then the second part is given by this difference. And in this difference, you see this is scaling invariant. So it's a total mean curvature normalized by the area radius. So that's scaling invariant. That term appears here as well. So it's scaling invariant. And therefore one would expect that whatever that quantity is, this guy got to be scaling invariant, which is the case. So this quantity, delta gamma, only depends on the metric. It's scaling invariant. It satisfies that if the metric is round, then this quantity is 0. Moreover, if the metric becomes rounder in the sense that if this pinch, if this quotient condition, right, the maximum of Gauss curvature compare over minimum of Gauss curvature, if this ratio goes to 1, then we can estimate that this quantity delta gamma tends to 0. One can compare this estimate with the previous estimate 10. So you see that in the round sphere case, the estimate reduced to 10 exactly because delta gamma is 0. And also, if the L1 norm of the mean curvature is small, say it goes to 0, then this bound tends to the 1/2 radius bound in Mentolithius-Shen's estimate. I'll mention a brief geometric implication, then I will stop. Then that will be the end of the talk. So say, for example, the following consideration is really a general considerations based on the fact that whenever you have a upper estimate on the Bartnik mass, essentially you give an estimate on the so-called Bray inner mass defined using inner horizons. To make that more precise, so basically one can consider the following configuration. You consider a configuration where where the Riemannian Penrose inequality holds, and physically that's the initial data set. The in time symmetric case, consider an initial data set surrounding black hole. And if you look at infinity, you use mass to relate to the black hole area. That's Penrose inequality. Physically, you may ask what happens if you take a body surrounding the black hole, the horizon. Is there a way of relating the black hole information to this finite body? And here is an implication. Once you have an upper estimate of the Bartnik mass. So in this configuration, if you have a body sigma surrounding the black hole, sigma h, then the preceding estimate shows the black hole area would be less than or equal to the same quantity used in the Bartnik mass estimate. Now, I do want to mention the limitation of this estimate. So, one good feature of this estimate is that it does not resort to isometric embedding. Previous work along this in this scenario would resort to embed, say, sigma to a model space, say like Schwarzschild, and that's some work I had with Dr. Siyuan Lu. In this formulation, you do not need to invoke isometric embedding. However, the expense you pay is this quantity, delta gamma. So currently our estimate shows this one goes to 0 if the metric is round in the previous sense, where the pinch of the Gauss curvature tends to 1. So in particular, a priori, if your body or surrounding horizon is very far from round, then we do not know how big this delta gamma can be. So in that case, this estimate may not give anything useful. So such an estimate only gives useful information if sigma is relatively round with respect to the corresponding mean curvature quantity. And I'll stop. And that's the end of my talk. And thank you.
All right, let's thank Pengzi. All right, are there any questions?
This is Christina. I have a question.
Yes, Christina. Yes, please.
If you could go back to your slide about, let me remember the slide. Sorry, it's near the beginning. I'm sliding back through my images.
I'm trying to get used to how to use this the arrow too. Yes, so the very beginning. Yes.
Okay, so I wrote questions down that I want to ask later. So you have this this mass where you have the mean curvature and the subtracting the mean curvature of the coordinate system. It's slide number, I don't know.
Well,
It says twice h minus h bar h.
okay, that's in
Detecting
the
mass, yeah.
right. That's in the asymptotic hyperbolic setting. Is that asymptotic flat or asymptotic?
Well, the change in the mean curvatures is, I think, the same formula either way.
Oh, okay. You mean the formula of the
Yeah.
It's different. It's probably different.
Yeah.
Okay.
Yeah. Okay. So in this sense, you're getting these formulas for the ADM mass that are taken using coordinate systems instead of having to find embeddings. This is sort of like the theme of your whole talk, I would say.
Yeah. Yes, you are right. Yeah, yes, you are right. So, right. So, okay. So, I think that. Okay, I think your comment is this. Right. So let's consider the cube case. And indeed, that's something I had in the. I had an impression which probably is wrong in the very first place. In the very first place, when I had this, I tend to think this, this at least heuristically looks like the analog of Brown-York mass, but it's not right. Even though this is a comparison of the physical quantity together with the mean curvature, which is 0 computed in the Euclidean case, and the angle, which is 90 degrees computed in the Euclidean case. However, these are not the quantity which arise from isometric embedding. So yes.
So if you were to decide on something like defining a canonical coordinate system of some sort. So for example, suppose you start with your cube-like shape or whatever shape you like to start with. Right. And you say something like, could I solve for a harmonic coordinate system inside the shape such that the mean curvature in the coordinate system is 0 so that it doesn't appear?
Right. Yeah.
Then maybe you could get some sort of new quasi-local mass. Right,
in a more geometric way, right? So here it still depends on the coordinate. And if, as you suggest, if one can construct such thing where the reference mean curvature is 0, then you have a more geometric expression on the right.
Yeah, so then maybe if so like in the Brown-York setting, there's we need to be able to find an isometric embedding, and in this case it would be we need to be able to find a coordinate system.
Yeah.
So I mean the two different challenges. The one is the Nuremberg kind of challenge that it exists, but what is it, so that you can actually evaluate it. And in this case it would be a different partial differential equations to solve to find a coordinate system that works, but maybe something like a harmonic coordinate system might exist under certain circumstances. So anyway, that's what I was just thought. That's just a thought I had.
Yeah. Well, thanks. I think there are. Yeah.
I think it has a lot of potential of being actually doable. I mean that one of the nice things I like about this is that if you have the coordinate system information, you can find out the actual values. But then to make it geometric or canonical, then you have to say, okay, this is a special coordinate system. So anyway, it's beautiful talk, beautiful stuff.
Oh, thank you.
Hey, Pengzi, could I just see the formula that you had in one of the last slides?
Yeah, sure. Yes. Let me
upper bound on Bartnik.
Okay, right. Let me try to make use one of the arrow to see if I can get there very quick. Okay, this seems to yes, maybe this one. Yeah. So yeah. Let me erase those. Yeah. Is this good? Done.
Yeah. Okay. So I guess what I'm trying to figure out, does it follow from this that given a fixed gamma,
right? If you fix gamma.
Yeah, fix a gamma. Does it follow from this that there's some L1 integral of h that prevents you from being able to do non-negative scalar curvature fill-ins?
Yeah, that's very good. Yeah, that's exactly what. Yeah, I mean, I want what this shows. I mean, what this can be used for if it produces that result. So in other words, any bound on the Bartnik mass from above would presumably produce a necessary condition for the data to allow non-negative scalar curvature filling in. Now, unfortunately, in this case, one would run into the same concern that I mentioned in the next slide. So if the metric is the one that I draw here, if it's far from being round, then this quantity then
Oh, right. Okay.
right, yeah, then this quantity will be bigger than
Got it.
0. Right, yeah. So in other words, yes, it provides some necessary condition for the data to admit non-negative scalar curvature filling in if this quantity competes with the total mean curvature. Yeah. So in other words, if you fix the metric, then one would say then the total mean curvature cannot be relatively large for this data to admit a non-negative scalar curvature filling in, and which is kind of consistent with what Shitan's result says. Shitan's result says if it admits a non-negative scalar curvature filling in, then the maximum of the total mean curvature is a Euclidean one.
Yeah. Okay. Thanks.
So in other words, this estimate, I do not claim this is optimal. So for this general case, 12, I think it's far from being optimum in the general case. The previous one in a special setting that when the metric is round, I think this 10 is optimal, but only in this very special case. So in general, I think how to refine, how to get a more precise estimate is still very challenging.
All right, thank you.
All right, thanks, Dan.